Okay, this video will be about gluconeogenesis. Now, before we get into the actual reactions and regulation that's involved in gluconeogenesis, we need to examine why and the purpose of gluconeogenesis. Remember that gluconeogenesis occurs primarily in the liver in a fasting state. Now, the reason we need gluconeogenesis is because over time, as we enter a longer fasting period, our glucose availability declines from the blood and from our glycogen stores, and the glucose needs to be restored primarily through gluconeogenesis. So let's consider our daily needs for glucose. Now, when I say daily, I'm considering approximately a 24-hour period, and this 24-hour period is considering normal activity. We're not talking about marathon running. So under every 24-hour period, our whole body is going to need to oxidize 160 grams of glucose per day. And this is to maintain normal whole body homeostasis. Maybe even more important, consider that our brain is going to need approximately 120 grams of glucose in order to properly function. The brain activity is not going to change at any appreciable time during day or night, so this is a constant utilization of glucose. So this accounts for approximately 280 grams of glucose per day that is required for the body to maintain normal homeostatic balance. Now let's look at the other part. The other part of the equation is glucose availability. Glucose availability. Body fluids. Body fluids include the blood, tissue fluids, etc. These account for approximately 20 grams of glucose availability. Total glycogen stores, which are the main supply of glucose during a fasting state, this accounts for 190 grams of glucose. If we add these up, we see in a 24-hour period we have approximately 210 grams of glucose availability. Compare this with our need for 280 grams of glucose. The numbers don't match, so that means that we have to make up for that extra amount of glucose that is required during a 24-hour fasting period. Also keep in mind that in an exercise state, this is going to be even higher requirement. Now the next thing is, let's turn this into a graph so that we can see the timing of gluconeogenesis. So if we look here on the y-axis of glucose oxidized, we can see that during the brief fed state that we are normally in, because remember we're normally in a fasting state, we have ingested glucose, and glucose oxidation of the ingested glucose goes down over the fasting state. And the reason for this is, first of all, we are restoring our energy needs because we are just coming out of a fasting state. So remember, the first thing the cell is going to do is restore its energy level to the highest ATP levels it can. The other reason that this declines rapidly is because we are removing glucose from the circulation, and we are storing this as glycogen in muscle and liver. So the glucose oxidation of the glucose that is ingested during a fed period is disappearing out of the bloodstream. Now let's consider the beginning of our fasting period. Remember, fasting equals glucagon signaling. Glucagon signaling is going to initiate glycogenolysis. So this is glycogenolysis. And the glucagon is signaling that we are in a fasting state, and our glucose utilization is going to continue, but the glucose from a fed state is now in storage in liver. So glycogenolysis in the liver will restore the glucose back into the circulation so we can continue satisfying our glucose needs. Now, as we continue our fast, the glycogen stores will eventually disappear. And if we consider this period of time when our glycogen stores are being utilized, this is probably 18 to about 20 hours depending on physical activity. So greater physical activity means that this amount of time will be shorter. So when we get to this point, our glucose availability starts to become compromised because our glycogen stores in the liver primarily are essentially depleted. So in order to prepare for this, the body begins gluconeogenesis back here at the beginning of the fed state, beginning of the fasting state. Gluconeogenesis increases over time so that now we have a compensation, this amount here. The gluconeogenesis is compensating for the lack of glucose coming out of the liver because of release of glycogen stores. So this is the body's way of preparing for a very long-term fast. Now eventually what we're going to see is that the gluconeogenesis is going to decline. This decline is called glucose sparing. And this is basically a reaction to give the liver a break, to reduce its glucose generation reactions, and the difference in energy here needs to be compensated. And so it's being compensated by the availability of another fuel source, which are ketones, and we'll talk about this next week. Once we start getting into this region here, out to ketones and beyond, which is approximately 30 to 40 days, now this is considered the starvation period. And we'll talk more about this when we get into amino acid metabolism. So that's the purpose and the reason why we need gluconeogenesis. It's primarily to compensate for long-term fasting periods, and the liver again is the altruistic organ that's going to supply this. Now the next video I'll start a new one, and then we'll get into the reactions and the regulation of each step involved in gluconeogenesis.